This takes forever in computing terms, on the computing scale, and so it's not a practical way to train a big neural network. You can imagine, instead of just rolling down to the bottom of a simple valley, we have a very high dimensional valley, and we have to find our way down. And because there are so many dimensions, one for each of these weights, that the computation just becomes prohibitively expensive. Luckily, there was an insight that lets us do this in a very reasonable time. And that's that if we're careful about how we design our neural network, we can calculate the slope directly, the gradient. We can figure out the direction that we need to adjust the weight without going all the way back through our neural network and recalculating. So just to review, the slope that we're talking about is when we make a change in weight, the error will change a little bit, and that relation of the change in weight to the change in error is the slope. Mathematically, there are several ways to write this. We'll favor the one on the bottom. It's technically most correct. We'll call it TEDW for shorthand. Every time you see it, just think the change in error when I change a weight, or the change in the thing on the top when I change the thing on the bottom. This does get into a little bit of calculus. We do take derivatives. That's how we calculate slope. If it's new to you, I strongly recommend a good semester of calculus just because the concepts are so universal. And a lot of them have very nice physical interpretations, which I find very appealing. But don't worry, otherwise just gloss over this and pay attention to the rest, and you'll get a general sense for how this works. So in this case, if we change the weight by +1, the error changes by -2, which gives us a slope of -2. That tells us the direction that we should adjust our weight and how much we should adjust it to bring the error down. Now to do this, you have to know what your error function is. So assume we had an error function that was the square of the weight, and you can see that our weight is right at -1. So the first thing we do is we take the derivative, change in error, divided by change in weight, TEDW. The derivative of weight squared is 2 times the weight. And so we plug in our weight of -1, and we get a slope, TEDW, of -2. Now the other trick that lets us do this with deep neural networks is chaining. And to show you how this works, imagine a very simple, trivial neural network with just one hidden layer, one input layer, one output layer, and one weight connecting each of them. So it's obvious to see that the value y is just the value x times the weight connecting them, W1. So if we change W1 a little bit, we just take the derivative of y with respect to W1, and we get x. The slope is x. If I change W1 by a little bit, then y will change by x times the size of that adjustment. Similarly, for the next step, we can see that E is just the value y times the weight W2. And so when we calculate DE/dy, it's just W2. Because this network is so simple, we can calculate from one edge to the other. X times W1 times W2 is the error of E. And so if we want to calculate how much will the error change if I change W1, we just take the derivative of that with respect to W1 and get X times W2. So this illustrates, you can see here now, that what we just calculated is actually the product of our first derivative that we took, the dy dw1, times the derivative for the next step, de dy, multiplied together. This is chaining. You can calculate the slope of each tiny step and then multiply all of those together to get the slope of the full chain, derivative of the full chain. So in a deeper neural network, what this would look like is if I want to know how much the error will change if I adjust a weight that's deep in the network, I just calculate the derivative of each tiny little step all the way back to the weight that I'm trying to calculate, and then multiply them all together. This computationally is many, many times cheaper than what we had to do before of recalculating the error for the whole neural network for every weight. Now, in the neural network that we've created, there are several types of backpropagation we have to do. There's several operations we have to do. For each one of those, we have to be able to calculate the slope. So for the first one, it's just a weighted connection between two neurons, A and B. So let's assume we know the change in error with respect to B. We want to know the change in error with respect to A. To get there, we need to know dB dA. So to get that, we just write the relationship between D and A, take the derivative of B with respect to A, we get the weight, W, and now we know how to make that step. We know how to do that little nugget of backpropagation. Another element that we've seen is sums. All of our neurons sum up a lot of inputs. So take this backpropagation step. We do the same thing. We write our expression, and then we take the derivative of our endpoint, Z, with respect to our step that we're propagating to A, and dZBA, in this case, is just 1. Which makes sense. If we have a sum of a whole bunch of elements, we increase one of those elements by 1, we expect the sum to increase by 1. That's the definition of a slope of 1. 1-to-1 relation there. Another element that we have that we need to be able to backpropagate is the sigmoid function.